Hello everyone. Tonight, we're going to visit a galaxy that feels like a neighbor. Not because it's close in any ordinary sense, but because it's close enough to be familiar. Andromeda, Messier 31, a spiral galaxy large and luminous, hanging in the northern sky, and destined far in the future to mingle with the Milky Way. For decades, Andromeda has been a kind of mirror, a way to study a big spiral galaxy from the outside, the way we can't quite study our own because we live inside it. And now, James Webb Space Telescope has added something new to this relationship. Webb doesn't simply take prettier pictures. It changes what is measurable. It pushes deeper into dust. It separates stars in crowded fields. It sees the cool glow of molecules and warm dust that older telescopes could only hint at. It turns Andromeda from a postcard into a textured landscape. So, tonight, we'll move slowly through Webb's most important recent findings and observational themes in Andromeda. We'll talk about what Webb has actually observed. What kinds of measurements are now possible? What astronomers are learning about Andromeda's dust, star formation, star clusters, and stellar populations. And we'll do it in a calm way, like a guided night walk through a city you've never visited but somehow recognize. Because the truth is that Andromeda is not just out there. It's part of the same cosmic ecology as us, a sibling galaxy, a future dance partner, a laboratory for understanding how spiral galaxies live, age, and change. Settle in, let your breathing slow, and imagine the telescope, far from Earth, quietly collecting photons that have been traveling for 2.5 million years. Light that left Andromeda before humans built cities, before writing, before agriculture. Light that arrives now and becomes knowledge. What James Webb is actually good at, and why Andromeda is a perfect target. To understand Webb's latest detections, it helps to understand Webb's special strengths. Webb is, above all, an infrared observatory. It sees light longer in wavelength than what your eyes see. That matters because infrared light can slip through dust more easily than visible light. Dust is not just dirt in space. It is a complex mix of tiny grains, often carbon-rich or silicate-rich, sometimes coated in ices, sometimes mixed with complex molecules. Dust absorbs and scatters visible light, hiding star formation regions like curtains hiding a bright room. But in the infrared, the curtains become thinner, not transparent, not irrelevant, but much less dominant. This is why Webb is transformative for galaxies like Andromeda, which contains thick dust lanes, star-forming rings, and crowded inner regions. Webb has 3 core instrument families that show up again and again in Andromeda work. NIRCam, Webb's near-infrared camera, is the big map maker. It produces sharp images and resolves stars in regions that are extremely crowded. It can also reveal dust structures as silhouettes and as faint glow, depending on wavelength. NIRSpec is the near-infrared spectrograph. It doesn't just take a picture. It spreads light into a spectrum, letting scientists identify chemical fingerprints and physical conditions, temperatures, densities, ionization states, and motion through Doppler shifts. MIRI, the mid-infrared instrument, is Webb's view into warm dust and complex molecules. It sees emission from polycyclic aromatic hydrocarbons, often called PAHs, which are large carbon-based molecules that glow in the mid-infrared when excited by starlight. MIRI is especially valuable for studying how star formation interacts with its dusty environment. Andromeda is a perfect testbed for Webb because it offers something rare: a whole large spiral galaxy, close enough that we can resolve individual stars and star clusters across wide areas, while still seeing the galaxy as an external system with a coherent structure. In many galaxies, you either get a wide view with no detail or detail in a tiny patch. Andromeda offers both. And because Andromeda has been studied extensively with earlier observatories, Webb's new data can be compared and calibrated against decades of existing measurements. That combination, proximity and context, makes Webb's recent Andromeda work unusually powerful. The most important shift: from pretty dust lanes to measurable dust physics. One of Webb's biggest recent contributions in Andromeda is a more complete, more physically grounded view of dust. In older visible images, dust shows up mostly as dark lanes. Beautiful, dramatic, and frustrating. You see where dust blocks light, but you don't easily see what the dust is doing, or how it is mixed with gas, or how it is being processed by radiation and shocks. In the infrared, dust becomes a multi-layer story. At shorter near-infrared wavelengths, you can see stars behind dust that were previously obscured. That allows astronomers to build much better maps of how much dust extinction exists in different parts of Andromeda. At longer wavelengths, especially with MIRI, dust becomes a glow, not starlight, but thermal emission and molecular features. This glow reveals where dust is being heated, where complex molecules survive, and where the interstellar medium is actively shaped by star formation. In the recent Webb-era view, Andromeda's dust is not just a set of lanes. It is a network. Filaments, shells, knots, bubbles, thin tendrils where magnetic fields may help organize material, thicker ridges where spiral density waves compress gas, and a striking ring-like structure in the star-forming disk, often described as a ring around the central region, that becomes especially interesting when seen with Webb's resolution and wavelength coverage. The major scientific theme here is not merely there is dust. It is that the dust appears to be actively processed. Grains grow, fragment, and change composition. Harsh radiation fields can break down complex molecules. Shocks from supernova remnants can destroy grains or alter them. Dense clouds can shield molecules and allow them to persist. Webb's mid-infrared sensitivity allows astronomers to map where PAH emission is strong and where it is weak, and to compare that to star-forming tracers and to the distribution of older stellar populations. One of the subtle but important latest detections here is the ability to separate environments that look similar in visible light but are physically different. Two dark dust lanes might block the same amount of visible light, yet one might be warm, molecule-rich, actively forming stars, and the other might be colder, more quiescent, and simply sitting between us and a bright background. Webb lets those differences emerge, and in a galaxy-wide context, those differences become clues to Andromeda's overall pace of star formation, its efficiency, and its recent history. The star-forming ring, a familiar structure, newly revealed in detail. If you've ever seen Andromeda in images, you may have heard about its ring-like star-forming structure. In broad terms, Andromeda's current star formation is not evenly distributed. It is concentrated in certain regions, with a prominent ring-like feature that has been studied in multiple wavelengths. Webb's recent imaging and mid-infrared mapping add finer detail. In Webb's view, the ring becomes less like a simple circle and more like a living zone. Clumps embedded in filaments, regions that are bright in dust emission but not necessarily equally bright in visible starlight. Pockets that suggest embedded star formation, young stars still partly hidden inside their natal clouds. And in some parts of the ring, you can see evidence of feedback shaping the medium. Cavities and arcs where stellar winds and previous supernovae may have pushed gas outward, leaving shells of compressed material around the edges. This matters because Andromeda is often described as a relatively quiet spiral compared to more vigorously star-forming galaxies. It is not a classic starburst galaxy. Its star formation rate is modest. And yet, within that modest global rate, there are concentrated regions where the local physics is intense. Radiation fields, dust heating, and the complex survival of molecules. Webb allows astronomers to examine these environments in a galaxy that is both large and near enough for detailed mapping. And in Andromeda, the ring is particularly valuable because it can encode history. Rings can be driven by resonances in a galaxy's gravitational potential. They can also be influenced by interactions, including past encounters with satellite galaxies. Andromeda has satellites, and it has evidence of past mergers and accretion events. So, when Webb reveals intricate ring substructure, it doesn't only tell us where stars are forming, it hints at why this pattern exists. In the Webb era, a key direction of research is to combine infrared mapping of dust and star formation with dynamical models of Andromeda's disk to determine which processes best explain the ring's geometry and the distribution of star-forming clumps. Even when the final answer remains uncertain, the new data tighten the constraints, and tightening constraints is one of the quiet triumphs of good astronomy. Resolving stars in crowded regions, Andromeda becomes a city of individual lights. Another major Webb contribution is stellar resolution in places that are challenging for other telescopes. Andromeda is close, but it is still far enough that individual stars can blend together in dense regions, especially near the bulge and inner disk. Blending is a problem because it biases measurements. If many stars appear as one, you might overestimate brightness and misclassify the type of star you are seeing. Webb's sharp imaging in the near-infrared helps cut through this crowding. This enables better measurements of stellar populations, ages, metallicities, and the distribution of evolved stars. Evolved stars matter a great deal. They are time capsules. Red giant branch stars, asymptotic giant branch stars, red supergiants. Each group appears at particular stages of stellar evolution and tells you about the star formation history of that region. In Andromeda, Webb can detect and classify large numbers of these stars in areas where dust and crowding make visible light studies harder. This leads to a set of latest results that are less about a single headline and more about a new level of clarity. More accurate star counts across different environments, better separation of different evolutionary phases, more reliable color magnitude diagrams in infrared bands, which can be combined with existing optical data from Hubble to create a multi-wavelength portrait of stellar ages and compositions. In practical terms, Webb helps astronomers answer questions like these. How does the bulge population differ from the disk population? What is the gradient of metallicity across Andromeda's disk? How much intermediate age population exists in various regions? And what does that imply about star formation episodes over the last few billion years? How patchy is dust extinction, and how does it bias older surveys? These are not glamorous questions to a casual viewer, but they are foundational. They are the difference between knowing a galaxy's appearance and knowing its biography. And Webb's biography writing ability, especially in crowded and dusty regions, is one of the most important new developments for Andromeda science. Star clusters in Andromeda, Webb as a microscope for galactic archaeology. Andromeda is rich in star clusters. There are open clusters in the disk and a large population of globular clusters in the halo and bulge. Globular clusters are especially valuable as archaeological artifacts. They are old. They preserve chemical and dynamical history. They can reveal the assembly of a galaxy, what it formed internally, what it accreted from smaller galaxies, and how its halo grew over time. Webb's resolution and infrared sensitivity help in a few ways. It can resolve stars in clusters that were previously too crowded, improving age and metallicity estimates. It can see through dust that might obscure clusters in the disk. It can also measure the integrated light of clusters at wavelengths that highlight certain stellar populations, such as cool giants. When paired with spectroscopy, this can provide chemical fingerprints. In the latest Andromeda work, one recurring theme is disentangling the origin of cluster subpopulations. Some clusters may have formed in Andromeda's early phases. Others may have been accreted during mergers. The chemical composition of a cluster, its orbit, and its age can hint at its origin. Webb does not solve this alone, but it adds decisive information to the puzzle by improving photometry in crowded fields and extending the wavelength range into the infrared. Another quiet advantage of Webb is that infrared observations can be less sensitive to certain stellar atmosphere complexities that complicate optical colors, especially when dust reddening is severe. That doesn't remove all uncertainties, but it can make cluster parameters more robust in dusty environments. So, when someone asks, what are Webb's latest detections in Andromeda? A good, scientifically honest answer includes this. Webb is enabling a more accurate census and characterization of Andromeda's star clusters, which feeds directly into a more accurate history of how Andromeda assembled over time. That is not a single dramatic discovery. It is a systematic upgrade in our ability to read the galaxy's fossil record. The nucleus and central region, a complicated heart, seen in new wavelengths. Andromeda's center is famously complex. It contains a supermassive black hole, and it has an unusual nuclear structure that has been interpreted as involving multiple brightness peaks and a dynamically interesting central configuration. The central region is also dusty and crowded, which makes near-infrared observation particularly valuable. Webb's contributions here tend to fall into two categories: sharper imaging of the stellar distribution and infrared spectroscopy that can probe stellar content and interstellar material. With sharp near-infrared imaging, astronomers can better trace where stars dominate and where dust lanes cut through. They can map how the light profile changes with wavelength, which helps separate stellar populations from dust effects. Spectroscopy can measure absorption features from stellar atmospheres and emission features from gas and dust, which helps constrain the ages and metallicities of the central populations and the state of the interstellar medium in the nucleus. A key theme in modern galaxy centers is that they are not static. Gas can flow inward. Star formation can occur in bursts. Black hole accretion can flare and fade. Feedback can heat, ionize, and push gas. And while Andromeda's central black hole is not currently in a bright quasar phase, the environment can still show evidence of past activity, and it certainly shows the imprint of dynamics. Webb's infrared data provide an additional layer for separating the components of the central region. What fraction of the light comes from older bulge stars? What fraction is affected by dust extinction? Where is warm dust located? Are there localized regions of emission that indicate specific physical conditions? These questions are often answered incrementally by careful modeling and comparison to earlier data from Hubble, Spitzer, ground-based telescopes, and radio observations. Webb adds a sharper and more dust-penetrating view to that multi-instrument narrative. Planetary nebulae, evolved stars, and the recycling of matter. Galaxies are not only places where stars are born. They are places where stars die, gently or violently, and return material to the interstellar medium. In a galaxy like Andromeda, the recycling of matter is continuous. Evolved stars shed mass through winds. Planetary nebulae form when certain stars expel their outer layers and the exposed core ionizes the ejected gas. Supernovae enrich the medium with heavy elements and shocks. Webb's infrared sensitivity is excellent for studying dusty envelopes around evolved stars and for detecting certain emission features from dust and molecules. In Andromeda, this supports a better census of mass-losing stars, especially in regions where dust obscuration makes optical identification incomplete. This matters because mass loss from evolved stars is part of the galaxy's internal ecology. It contributes dust and gas back into the medium. It affects future star formation potential. It changes the dust-to-gas ratio in different environments. It contributes to the chemical evolution of the galaxy. When astronomers speak about latest Webb detections, sometimes what they mean is that certain categories of objects become easier to identify. Dusty AGB stars that are faint in optical bands but bright in infrared. Embedded sources that are heavily obscured. Structures shaped by circumstellar dust. And once those populations are better measured, models of Andromeda's infrared light become better grounded. That, in turn, improves measurements of star formation rates and dust properties because you can separate emission from star-forming regions and emission from evolved stars more cleanly. This is a subtle but important scientific upgrade. Less confusion, less mixing of signals, more accurate physical interpretation. Supernova remnants and energetic feedback, traces of old explosions in infrared light. Supernova remnants are expanding shock waves moving through the interstellar medium. They are laboratories for high-energy physics, plasma processes, dust destruction, and cosmic ray acceleration. In galaxies beyond the Milky Way, supernova remnants can be hard to study in detail, but Andromeda is close enough to allow targeted observations. Infrared observations are valuable because shocks can heat dust and excite certain emission lines. Webb can detect warm dust emission and, with spectroscopy, identify lines that trace shock conditions and ionization states. In practice, supernova remnant studies often combine X-ray data, optical emission line imaging, radio observations, and now Webb's infrared view. The latest part is Webb's ability to add spatially resolved mid-infrared information where dust is present, where it has been destroyed, where it is heated, and how shock fronts interact with dense clouds. In Andromeda, this helps build a more complete picture of how stellar death shapes the star-forming medium. It also feeds into a bigger question: why Andromeda's global star formation is relatively modest compared to some other spirals. Feedback processes and the state of the interstellar medium play a role. If gas is heated, dispersed, or stabilized against collapse, star formation can be suppressed. Webb doesn't deliver a single, simple answer, but it adds high-quality evidence about the physical state of dusty gas in multiple environments. Measuring star formation properly, why infrared changes the accounting. If you measure star formation using ultraviolet or visible light, you can miss what is hidden in dust. A young star cluster may be bright, but if it is embedded in a dusty cloud, its visible light is absorbed and re-emitted in the infrared. This is why infrared is crucial for star formation studies. Webb's ability to map Andromeda in near and mid-infrared allows astronomers to build a more complete census of star formation activity, especially the obscured component. And this matters in Andromeda because its star formation is not uniformly distributed and is intertwined with complex dust structures. In the Webb era, a major theme is combining different tracers, near-infrared star counts, and stellar population synthesis, mid-infrared dust and PAH emission, optical H-alpha emission for ionized gas, far infrared and sub-millimeter for cold dust from other observatories, radio for gas distribution and non-thermal processes. When these tracers are combined, astronomers can estimate not only where stars are forming, but how efficiently gas is converting into stars in different parts of the galaxy. Andromeda's relatively low star formation rate becomes more interesting when you can examine it region by region. Some regions may have plenty of gas, but low efficiency. Others may show signs of recent bursts. Others may show strong dust emission without corresponding high-mass star formation, hinting at heating by older stars or different interstellar conditions. Webb's latest detections include the ability to see these distinctions more clearly and to avoid oversimplified galaxy-wide averages. In a sense, Webb turns Andromeda from a single number into a map of varied neighborhoods. The interstellar medium as a living system, molecules, dust, and radiation fields. A galaxy is not just stars separated by emptiness. Between stars is the interstellar medium, gas in multiple phases and dust mixed throughout. Cold molecular clouds, warm neutral gas, hot ionized bubbles, and everything in between. Webb's mid-infrared capability is particularly valuable for tracing the interface between star-forming regions and their surroundings. PAH emission is one tracer of photodissociation regions, the boundary zones where ultraviolet light from young stars interacts with molecular clouds. In these zones, molecules can be dissociated, dust can be heated, and complex chemistry can occur. Mapping these features across Andromeda helps astronomers understand how radiation fields vary across the disk, how molecular material is structured, and how star formation proceeds in a relatively quiescent spiral. Another key aspect is dust grain evolution. Dust grains can be destroyed by shocks or intense radiation, and they can grow by coagulation in dense regions. The balance of these processes changes the infrared emission spectrum. Webb's spectroscopy can help constrain these properties in selected regions, making it possible to compare Andromeda's interstellar chemistry and dust physics to those of the Milky Way and other nearby galaxies. This comparison is scientifically valuable because we often assume the Milky Way is typical, but we don't actually know that without external reference points. Andromeda provides a reference point that is both similar and different, a large spiral, but with its own merger history, its own star formation behavior, its own structure. So Webb's Andromeda work is partly a story about Andromeda itself, and partly a story about calibrating what normal spiral galaxy means. The halo and outer disk, faint structures, old stars, and the memory of mergers. Andromeda's halo contains streams and substructures, evidence of past mergers and accretion of smaller galaxies. These features have been studied with other telescopes, especially in optical surveys that map resolved stars and identify coherent streams. Webb's contribution here is more specialized because Webb's field of view is not designed for ultra-wide mapping the way some survey telescopes are, but Webb can provide deep, precise photometry and infrared information in selected halo fields. This can improve the characterization of stellar populations in streams and halo substructures, especially for older and dust-affected populations, and it can refine distances and metallicities in ways that complement optical data. In galactic archaeology, you often proceed like this. Wide surveys find structures. Targeted deep observations reveal their detailed composition. Webb is one of the most powerful targeted tools we have for such follow-up. So while Webb is not mapping the entire Andromeda halo in one giant project the way a dedicated survey would, it is capable of delivering high-quality, deep measurements in key regions that help decode Andromeda's assembly history. And that assembly history matters because Andromeda and the Milky Way are not identical. Andromeda appears to have had a more active merger history in some interpretations, and its stellar halo may be richer in substructure. Understanding these differences helps us understand the range of evolutionary paths for large spirals. It also helps us place the Milky Way's history into context. A realistic note on latest findings. Astronomy moves by careful increments. There is a temptation, especially online, to treat every new Webb image as a dramatic new discovery. Sometimes that happens, but more often, real progress looks like this. A new dataset improves resolution and wavelength coverage. Scientists remeasure things that were measured before, but with less uncertainty. They find that some earlier conclusions were correct, but now better supported. They find that some earlier conclusions were partly biased by dust or blending. They refine models of stellar populations. They separate signals that were previously mixed. They build better physical maps that connect dust emission, star formation, and stellar ages. This is the kind of progress Webb delivers for Andromeda, and it is not lesser progress because it is incremental. In many fields, especially those involving complex systems, better constraints are the difference between plausible stories and testable science. So, when you hear Webb's latest detections in Andromeda, it is often more accurate to think Webb is making Andromeda measurable in more dimensions, not just where things are, but what they are, how they are heated, how old they are, how dusty the line of sight is, and how different environments compare. That is the calm revolution. What Webb has clarified about Andromeda's personality as a galaxy. Andromeda has long been considered a somewhat unusual neighbor in one respect. For a big spiral, it forms stars at a modest rate. It has star formation, yes, but it is not as actively forming stars as some similar-looking galaxies. It also has a prominent bulge and evidence of past interactions. Webb's infrared view reinforces the idea that Andromeda's interstellar medium is structured and active in localized regions, especially in ring-like features and dust lanes. But the galaxy as a whole is not in a high-intensity starburst mode. This combination suggests an ecosystem where gas exists and cycles, dust exists and is processed, star formation continues, but perhaps with lower efficiency or different regulation than in more vigorously star-forming spirals. There are multiple possible contributors: the stability of the disk, the distribution of molecular gas, the effect of shear and dynamics, the influence of past mergers, the role of feedback, the availability of cold, dense gas. Webb doesn't pick one answer, but it provides the detailed environmental data that any good answer must match. In Andromeda, Webb makes it easier to ask a sharper question. Not, is Andromeda forming stars? But where exactly is Andromeda forming stars? In what physical conditions? And why those conditions exist in those places? That is a question worthy of a giant telescope. How Webb data is combined with other observatories to create the full Andromeda. A telescope is never the whole story. Andromeda is best understood when Webb's data is combined with data from many sources. Hubble provides exquisite optical resolution and decades of resolved star surveys. Spitzer provided earlier infrared mapping at lower resolution, which is valuable for comparison and for large-scale context. Galax provided ultraviolet maps of recent star formation. ALMA and other radio observatories map molecular gas and cold dust in selected regions. Large area ground-based surveys map Andromeda's extended halo in streams. X-ray observatories reveal hot gas, X-ray binaries, supernova remnants, and energetic processes. When Webb enters this ecosystem, it often plays the role of the bridge. It links the optical view of stars and dust extinction to the mid-infrared view of dust emission and molecules. It resolves structures that were blurred in earlier infrared surveys. It provides spectroscopy that can diagnose conditions in dusty regions. So Webb's latest findings in Andromeda are often not a standalone narrative. They are the missing pieces that make multi-wavelength models coherent. And coherence is powerful. When different wavelengths tell the same story, confidence rises. When they disagree, new physics is revealed, or new biases are discovered. Either outcome advances the field. A gentle tour of the kinds of new details Webb reveals, without forcing a single headline. If you were to drift over Andromeda with Webb's eyes, you would notice several kinds of details that represent genuine advances. You would see dust lanes breaking into finer filaments. You would see star-forming regions that were previously smeared together, separate into distinct knots. You would see warm dust tracing the edges of cavities carved by feedback. You would see PA emission outlining photodissociation regions like a faint, glowing border. You would notice that some regions bright in visible starlight are not the same regions bright in mid-infrared, because older stars and dust heating can produce different patterns than young massive stars. You would see the bulge and inner disk in a way that reduces the dominance of dust extinction, allowing the underlying stellar distribution to be measured with less bias. You would resolve more individual stars in challenging fields, improving the statistics of stellar population studies. You would identify more dusty evolved stars and characterize their contribution to the galaxy's infrared light. You would see that Andromeda's quietness is not emptiness, but a different regime, structured, moderate, regulated. None of these is a single sensational claim, but together they form a strong summary of what Webb has changed for Andromeda. It has increased resolution where it matters. It has improved access to dusty regions. It has enabled more physical interpretation of the interstellar medium. It has made star formation mapping more complete. It has strengthened the archaeological readout of stellar populations and clusters. That is a lot. Quietly. The future angle, what astronomers are trying to answer next with Webb in Andromeda? It can be soothing to remember that astronomy is ongoing. Webb's Andromeda work is not finished. It is opening doors, and some of the most likely next directions are naturally suggested by what Webb does best: more detailed spectroscopy of selected star-forming regions to measure ionization conditions, metallicity, and dust properties. Better calibration of star formation tracers in a low to moderate star formation spiral using Webb's mid-infrared features in combination with other indicators. Targeted studies of the nucleus and inner bulge to refine models of the central structure, stellar populations, and dust distribution. Deeper observations of specific halo substructures to refine Andromeda's merger history and compare to simulations. Expanded cluster studies to better separate accreted clusters from in situ clusters using detailed photometry and, where possible, spectroscopy. Improved improved models of dust heating that separate contributions from young stars and older stars, which is essential for interpreting infrared emission in galaxies that are not dominated by starbursts. These are the kinds of questions that can occupy teams for years. And Andromeda is so important and so close that it is likely to remain a Webb target for a long time. A calm closing perspective. Why Andromeda matters and why Webb's view feels different. When you look at Andromeda with the unaided eye from a dark location, it looks like a faint smear, a suggestion of another island universe, a hint. And yet inside that smear are hundreds of billions of stars, dust lanes, molecular clouds, clusters, remnants of ancient mergers, and a central black hole. James Webb doesn't turn that smear into something simple. It turns it into something honest, complex, layered, full of structure that matches the complexity of a living galaxy. The latest detections are not a list of trophies. They are a change in texture, a change in what we can separate from what we can only blur together. A change in how well we can connect dust, gas, and stars into one coherent physical story. And in a quieter way, Webb changes how Andromeda feels. It becomes less like a distant object and more like a place. Not a place we can visit, but a place we can understand. A nearby spiral where the laws of physics unfold on a vast scale, yet in patterns we can map and interpret. So tonight, if you let your mind rest on one gentle takeaway, let it be this. Andromeda is still Andromeda, but Webb is teaching us how to read it better, not just as a shape in the sky, but as a dynamic system, a galaxy with a past written in streams and clusters, a present written in dust filaments and star-forming rings, and a future written in gravity, slowly drawing it toward the Milky Way across the dark. Photons leave Andromeda. They travel for millions of years. They arrive at a quiet telescope, and then, slowly, they become a clearer story. Sweet dreams.